The next speaker is Dr. Fei Yan. She's currently a postdoctoral researcher at Wall University. Her research interests includes modeling driver uncertainty, trust in automation, adaptive driver assistance in automated driving, across cross-cultural studies of driving behavior, building trust in automation considering driver uncertainty and system uncertainty. And yeah, will you please share the, yeah, here. And her topics building trust in automation considering driving uncertainty and the system uncertainty. So yeah.
Yeah, thanks for the
Give the
introduction. Hi everyone, I'm Fei Yan, and today I want to introduce you some work about the building of trust by considering driver uncertainty and system uncertainty. So I come from the Department of Human Factors at University, which is chaired by Professor Martin Baumann. So here we mainly focus on the human machine interaction in the driving context, and also the human-robot interaction regarding the interaction strategy and also the building of trust between them. So my work is mainly focusing on the driver uncertainty regarding the investigation of the modeling driver uncertainty and also the building of trust by considering driver uncertainty. So first, I will give you some theoretic background. It is known that drivers' decision-making process in lane change maneuvers involves uncertainty. And this kind of driver uncertainty can, on the one hand, cause long reaction time, which further influence traffic safety. And on the other hand, it can influence driver trust in assistance system. So in our work, driver uncertainty is defined based on the temporal uncertainty that describes the aspect of response selection, which is defined as driver's difficulty to decide whether to overtake or not, or to wait in a given lane change situation. And the idea of building trust by considering driver uncertainty is inspired by the emancipation theory of trust in social psychology, which is said that trust is considered as one of the solutions to the problem caused by social uncertainty, which means that when humans are uncertain in their social interaction with others, they tend to reduce this kind of uncertainty by trusting others. For example, if you arrive at an unknown city, you want to find an address without any navigation possibilities, and at that time you meet someone you don't know, you are quite uncertain where should you go, and that people tell you, I mean, quite certainly, just go straight. You may probably want to follow his, I mean, or her suggestion. When we transfer this kind of idea to the human machine interaction domain, it means that when humans are not certain and machine can at that time provide useful information, it is hoped that the trust can be built between human and the machine. So with this background, we aim to develop a model-based lane change decision-making system that can consider driver uncertainty during decision-making in lane change maneuvers. It means that this assistance system can provide useful information on time when drivers are uncertain, and provide information unobstructed when drivers is uncertain. So it is assumed that in this way, the trust can be built between them and also the traffic safety can be improved. To achieve this, we first investigate driver uncertainty in lane change maneuvers in the driving simulator, and then based on the collected data, we developed a model of driver uncertainty. The next step is we then integrate this kind of driver model in a driving simulator, and we conducted an evaluation study.
Yanfei, are you still here?
we wait for her for several seconds. I think I've got the presentation, but we need the presenter here.
Okay.
I'll ask her. We take a short break right now.
Sorry?
Good.
Yeah.
That's
Okay.
great. Let's
So
continue.
what's the problem? So you can't hear
I
me?
think it's the internet
Yeah.
problem. And we are on the 7th page, I think the 7th slide.
Okay. Okay, here. So where do I stop? The first step or?
Yeah, I think for between the first and second step, you can
Okay.
start
Sorry.
with the first
Okay.
one.
Okay. Great.
No
Sorry.
problem.
So we first investigate driver uncertainty in lane change maneuvers in our driving simulator, and then based on the collected data, we develop a model of uncertainty. Then in the next step, we integrate this driver uncertainty model in the driving simulator, and in the end, we did an evaluation study. I mean, to compare this proposed lane change assistance system with other references that didn't consider driver uncertainty regarding the traffic safety and also the building of trust. And in the first step, we studied the impact of the potential factors that influence driver uncertainty, such as closing speed and time to collision on driver uncertainty in lane change maneuvers. So here you drive on the two-lane German highways, and you follow a lead vehicle in front of you. After 4.5 seconds, you hear an acoustic signal, and at the same time, there will be a approaching vehicle appear in the left side mirror on the other lane. So then your task is to decide, okay, this is possible to do the lane change. If you think it is possible to do the lane change, then you need to show your decisions by steering to the left. If it's not possible, you need to brake. So after your actions, you need to rate your uncertainty during decision making. So from 1 to 5 in the keypad. So 1 means very uncertain and 5 means very certain. So after you're typing the keypad, then the one try will, finish, the next try will begin. So in this experiment, we have 29 participants and 8 of them are males. So we manipulate the time to collision and closing speed between the ego vehicle and the approaching vehicle. So the TTC is varied from 7 seconds to 18 seconds, and the closing speed between them are from 10 km/h to 20 km/h. What we measured is the reaction time between the signal you hear at the beginning and the action, either steering to left or brake, and also the subjective uncertainty score from 1 to 5. So each participant will experience 3 blocks, and each block have 135 tries. So here it shows you the result regarding the reaction time, which influence the traffic safety, and also the subject uncertainty score on the right of the slide. So regarding for the reaction time, the multiple polynomial regression was conducted, and it shows both the closing speed and TTC have a significant effect on driver uncertainty on reaction time. And it can also be seen that with the increase in closing speed, the maximal mean reaction time appears earlier. And regarding the subject uncertainty score, ordinal regression has been conducted, and it also shows that both factors can influence this subject rating of uncertainty significantly. And similarly, with the increase in closing speed, the minimum uncertainty score appears also earlier. So totally, we collected 8,600 data samples. So each sample includes distance gap, closing speeds, TTC, at time of given acoustic signal, and also time of reaction. In addition, we have also the subjective uncertainty scores. So the idea is that we use this kind of data to develop a model that can predict driver's uncertainty as certain or uncertain based on the variables that can potentially influence driver uncertainty. We decide for a Bayesian network with this transparency and also the possibility to interpret all parameters in terms of probabilities. So what we use for the model, the variables of interest are the TTC and distance gap between the ego vehicle and the approaching vehicle and other lane, and also the TTC and distance gap between the ego vehicle and the lead vehicle. We choose the tree argument naive based, this structure among the candidate structures, and also we do the model evaluation. It shows that the selected 10 classifier has an accuracy of around 0.78. So we then want to integrate this kind of model into a driving simulator, which means that we need the corresponding human-machine interface for that. So here we just show you example of our interface. So they are three abstract faces with the emotional expressions. So the transparent yes symbol will be shown when the lane change is safe and the driver is certain. And thus we show this system's conservative character through this transparent color, because actually in this time driver knows what to do, so just keep it quiet and not so active. But when the driver is uncertain and the lane change is still safe, then you will say that the green symbol with the yes, and which means that when driver is uncertain, the system will be active to help driver on time. So if the lane change is not safe, then regardless of driver is certain or uncertain, you will see the red no symbol, which show also the priority of the criticality aspect. So so these symbols will be directly show near the approaching rear vehicle in the left side mirror. So here you can see how it looks like in the driving simulator, and the size of the symbols will also be adaptive regarding the distance between the approaching vehicle and ego vehicle. So in the last step, we then compare this proposed lane change assistance that consider driver uncertainty with other reference systems. So here we have 20 participants who took part in our evaluation study. We have a replicated Latin square design. So we have totally 5 conditions. The first condition is no assistance system. So it's the same driving task as I introduced in the last experiment. And then there are 2 reference systems that they only have 2 symbols. So system A represents a defensive system. So either driver is certain or uncertain, it will always show this transparent yes symbol. And the reference system B is offensive systems. So either driver is certain or uncertain, he will always show the green yes symbol quite active. Then we have our proposed system say that means that it has three symbols, and it will adapt to driver uncertainty. When driver is certain, it will show the transparent yes symbol. When driver is uncertain, then this green yes symbol, and then the red symbol for the unsafe lane change. We also have another reference system. They also have 3 symbols. But for this system, it has a fixed time delay set, which means at the beginning, you always say the transparent yes symbol. Then after 1.2 seconds, you will see the green yes symbol. Yeah, to compare them. So for the results, we measure the reaction time and also the rate of agreement, which means the percentage of the participant who follow the system's advice, and also the follow time, how fast they follow the system's advice. We found that both the system C and system D can both the best system to reduce the reaction time and also to increase the rate of agreement and follow time. We have no finding regarding the difference between systems in the trust questionnaire. But what we have found in the additional interviews that all systems are helpful regarding in compare with no assistance, a baseline condition, and the system C, which is the proposed system, are the most trusted system compared to other three reference systems. So here is an example. You see that if the system, the learning system comes to drive on, the trust can be built between them. Although we don't have, we don't find the significant difference in the objective data, but here, so when you explicitly ask participants, they show their tendency to, to trust the third system, our proposed system more. For the other part, I want to talk about, the building of trust regarding the machine uncertainty. So there are already some very good work. So here we propose to spatially visualize sensor information for automated vehicles to increase the driver trust in automation. We to test this, we did a small video study in the lab with 17 participants, and the scenario is overtaking obstacles on the 2-lane rural road. And there are 3 videos you can see here on the bottom of the slides. The first video, you can see that so there will be a stopped obstacle in front of you, and there's no oncoming traffic or no approaching vehicle from behind. And in the second video, there will be oncoming traffic, and in the third video, there will be a approaching vehicle from behind. And the procedure is the participant need to watch the video for 15 seconds on the monitor, and then they will hear a beep sound, which indicates the transition to the user interface. So we have 3 user interface. So participants need to select actions. There is a stationary obstacle in front of you, and what we'll do now. So the interface will display different levels of machine uncertainty. And after their selection of actions, they need to fill in the trust acceptance and also the usability questionnaire. So this is so we have 3 user interface here. So this is the first one. It only shows you the instruction of your task and also the optional select actions, what you can do, either to stop, let the vehicle to stop the car, or secure the obstacle, or just you hand over the control to the driver. But there's no information regarding the system uncertainty. And in the second user face, the user interface 1, UI1, here, so there is an additional representation of the sensors reliability with either, so quite generally, either the front sensor works or the back sensor is, uncertain. And the proposed the user interface 2 is using the triangles to indicate the range of front or back radar sensors, and also use the green color to show the sensor is certain and the red color sensor is uncertain, and also the general display of the system uncertain, the same as the UI1. So we measure the reaction time for the 3 user interface, and we find that the first interface, so without any information regarding machine uncertainty, is has the shortest reaction time compared to other user interface. We then had a look at the selected actions. So they have 3 options, and we found that it is quite interesting that regarding the take over the control, you can see that so in the UI2, our proposed system, participants tend to take over the control mostly. It means that when they know more about details about the system answering, they tend to, yeah, more probably to take over the control themselves. So we don't find the expected, significant effect regarding the subjective trust, acceptance, or usability. So for many of the items, so UI0 and UI2 are both good, and for many of the items, UI0 is preferred. As said, it's a small study, but I think it's give us some implications how we can, present driver uncertainty without overloading, driver to show the best effect of, presenting system uncertainty. Yeah, that's the introduction from my part. I'm looking forward to your questions. Thank you.
Okay, so thank you very much for your presentation, and let's see whether there are any questions from both on site and online.
Yes, I hope.
Yeah.
Thank you very much for interesting talk. So I am interested in machine uncertainty part. Please show us. Please show us 20 second, 22. I think.
22. Yeah.
Yes. No.
This one, not this one.
Yes. So yeah. Yes, this one. So how? My question is, what kind of uncertainty do you assume, and how this interface works? Because I guess there are automated vehicle detect many obstacles and cars or something like this, and but this interface seems like to indicate the level of uncertainty in one dimension or something. So yeah, how this UI works?
Yeah, this presentation of driver uncertainty is regarding the spatial representation. It shows you the range of the radar sensor works. For example, here it shows you, okay, the front range, the front radar sensor works quite well, but the back radar sensor is now uncertain. So so it's a spatial variance. So means that we think it's more intuitive for the driver to think, okay, what is a relevant surrounding vehicles, in the front, which can be reflected by the front radar sensors, and there are should be some vehicles that's relevant for the back radar sensors. But so we make this kind of spatial representation. But I think the problem is we as a participants got more confused because they need this and to interpret that. So in the end, regarding the reaction time, they do spend a lot of time, I think, to make the decision when they see this user interface, and also when they know what does this mean, or when they see this in so detailed, read information, they tend to, to have the third option. They want to take over the control system. So, so that's very also interesting. The more you know about system or how it works, as it's become more transparent to the, to the participants. So usually you may have some kind of uncertainty, display regarding a scale from 0 to 100, but here give you a quite spatial representation that let you know more detail. But it turned out to be that you drivers are maybe a little more uncertain. They want to take over the control, and they want to drive themselves in the end. So yeah,
I understand. So because this slide shows sensor uncertainty. So I think the uncertainty can be defined by in a hierarchical way. Sensory uncertainty and recognition uncertainty or something like this. If we want to know about the recognition uncertainty, so you should the color on each recognized object. So this in front of the vehicle is certain, but this one is uncertain, something like this.
This is different levels, because I think sensor uncertainty is from the machine's perspective, but recognition uncertainty is from the driver's perspective. It's, the machine's perspective, also it shows you the presentation or how you present machine uncertainty will influence drivers, either, cognition or, so this kind of levels uncertainty. So this, I think this shows you the relationship between them, but they are different, but they are also connected with each other, definitively.
Okay. So, but what I wanted to mention is recognition uncertainty in machine. I mean, machine or every uses sensor to recognize something. So there is two kinds of hierarchical uncertainty. One is a sensor uncertainty. Even if the sensor works very well, sometimes it fails to recognize something. So
Also, I think I misunderstood your point. You mean the census recognition uncertainty, right? Okay. Yes.
Yeah.
Okay.
Yes. Okay, and
Yeah, I've got a question about also
okay, you
uncertainty.
go first. You go first.
Sorry. Yeah, I go first. I'm one of the motivators today, so I can go first.
Okay.
Yeah, I'm curious about the uncertainty question, how you ask the participants, because you have the objective behavior environment and also a question of the uncertainty. Do you just ask them?
You mean the driver uncertainty, right? The first part.
Yeah. The first part, and did you ask them directly? Do you feel uncertainty of the traffic environment or of your control, or you have a cover story of this question? Because I'm not sure if you because when I designed the questionnaires, I designed a question, and my supervisor told me you need to give a cover story of the question that make the participant don't know what you want to ask them directly. I'm not sure if you also consider this issue when you design the questions.
Yes, definitely. This is quite important. So we do give some cover story about what we mean. Because it's quite subjective when they understand driver uncertainty. So we tell them this is not about if your decision is correct or not, and it's about the difficulty you felt during your decision in the last trial. So yeah, so this is what so we give the same introduction for this question to all the participants, and to ensure that they have the common understanding of what we measured for the driver uncertainty here. And in the end, I think we got a quite and also got a quite good results, or regarding this part, the subjective rating part.
Okay, thanks.
Okay, so
Thanks.
then it's I have a question, and a very quick one. I also interested in your study, and I think you mentioned about acoustic signals in the first study. Yeah, and I'm also doing some research about this, and when we make some discussions, someone will suggest me that the acoustic signals may have somehow make it a hurry to the driver, that I will like hurry you to make the decision, to make the maybe lane change decision. And do you think that this is correlation with certainty things?
I don't really think so. I think it depends on how you give the instructions about this acoustic signal to the participants. So in our experiment, we explicitly told them they have no stress to do their decisions, and the acoustic signal is used to indicate that something happened in front, and you need to do the lane change. So this is just some kind of indication of something. Maybe there's a construction, or there's a broken vehicle in front, or there is an accident. There can be anything. It's just used as an indicator. I don't really see this kind of association between the signal itself and the driver is either hurry up or not. I think if you explain them, if you have worry, you can explain them to the participant a little more. Make it clear. And here the signal is also used to measure the reaction time, which is also works quite well. I mean, if you also use it for measuring time, so you can consider it.
Okay, thank you very much.
No problem.
Okay, so Hailong.
Yeah, I have a short question. Maybe I missed some information. And my question is, did you get some data or some result which is show the relationship between the uncertainty and trust, or the reaction time and trust? Did you?
We got results between the relationship between the uncertainty and the reaction time. So they are negatively correlated with each other. And directly between the uncertainty and trust, I have showed you that in objective data, we don't have, the both systems say, so our system and also the other system, which also have three symbols, work both quite well regarding reaction time, regarding the following rate, the rate of agreement or follow time. So they are both well. So it means that when driver experience these two systems, they make almost, maybe I think the interval between the, for the system D, so what we used maybe is quite similar to system C. That's why, from the behavior aspect, we don't have any we don't have big difference for, to distinguish system C and D. But actually from the subjective impression, it's quite obvious that they feel the difference. They feel the difference of between the system C and D. They feel, the system C maybe is more adaptive to their decision-making process, and they are more chosen by participants. But for this part, we only have the subjective, results.
Okay, I see. Thank you.
Thank you.